Okay, everyone, welcome to the Prelab for the Titration of Acids and Bases lab. Putting this online because I want to make sure that the time you have in the double period is used to your advantage by doing the actual titrations, and we're not caught too much up in the explaining the theory behind it. I'm going to leave this up on my site so that when you're doing the calculations, you can refer back to them. First of all, the purpose of this lab is twofold. You're going to be doing two things. First thing you're going to be doing is standardizing a sodium hydroxide solution. Now, I will be providing you with the sodium hydroxide solution. You're going to be getting about a liter of it. And this might seem like quite a lot, but we're not only using it for this particular lab. It's going to be a sodium hydroxide solution we'll come back to and use in pretty much any other acid-based lab we do from this point out to the end of the year. So what you're essentially going to do in this first portion is to determine the concentration really, really well, so that when we do those additional labs, you will know the concentration really, really well. But we're not finding molarity. We're actually going to be calculating normality. And one of the things I'll be talking about is what is normality and how can we calculate that. The second thing we're going to be doing in this lab is using this standardized NaOH solution to determine percent KHP in an unknown sample. KHP, which I will be talking about what it is, fundamentally what you need to know is it's an acid right now. I mean, what you need to know at this moment, KHP is an acid, stands for potassium hydrogen phthalate. It has one protonizable proton and it comes in solid form. So it's a little different from a lot of our other acids, which are liquids. Now, normality, because our first goal is to determine the normality of an NaOH solution. So what is normality? Normality is defined as the number of equivalents of a compound divided by the liters of solution. Hopefully, when you look at this, even if you don't know what equivalents are, you should see a similarity between normality and molarity, because molarity is moles of solute divided by liters of solution. Normality and molarity are related. They're related through the idea of the equivalent. An equivalent is essentially how many reacting parts a compound has. I use this very general phrase, reacting parts, because we don't need to only use equivalents in terms of acid-base chemistry. We're actually going to be using equivalents later in the year when we do a redox titration. And in redox, it's not H's, it's not protons and not hydroxide ions that are reacting, it's actually electrons. But the idea of the equivalent still holds true. How many reacting parts a compound has? In terms of acid-base chemistry, the reacting bits are the H pluses and the OH minuses. So we can look at an acid and we can look at how many H's it has, how many protonizable protons it has. If it has one protonizable proton, we say that that acid has one equivalent. If it has two protonizable protons, we say that that acid has two equivalents. Equivalents for bases, the number of hydroxides. Sodium hydroxide has one equivalent. If I pick a group 2 hydroxide, it will have two equivalents. Normality and molarity are related. Molarity is moles per liter. Moles does not take into account how many reacting bits something has. Molarity is just how many moles are there. But if you think about, for example, H2SO4, 1 mole of H2SO4 can produce 2 moles of hydrogen ions and a sulfate ion. So if I have, for example, and this is the classic example that people use when they talk about normality, 1 mole of this makes 2 moles of this. So a 1 molar solution of H2SO4 creates a 2 molar solution of H plus ion if it completely dissociates. So talking about the molarity of the H2SO4 doesn't really do me justice in terms of knowing just how much H plus I get. So molarity, if I multiply it by the number of reacting bits, gives me normality. Normality is molarity times the number of equivalents. H2SO4 has two equivalents. It has two reacting pieces. So whatever the molarity is, if this is 1 molar H2SO4, I could multiply it by 2 equivalents. That would give me a 2 normal solution of H2SO4. And yes, that is how we talk about normality. Just like molarity is molar, normality is normal. So just to make sure we understand this, because it's written down in PowerPoint form, NaOH has one equivalent. It has one equivalent because it has one hydroxide. That is the reacting bit from NaOH. The Na portion is not the thing that's going to do the reacting in acid-base chemistry. It's the hydroxide that does the reacting, and it has one of them. Calcium hydroxide has two equivalents. It has two reacting bits. A 0.1 molar sodium hydroxide solution is also 0.1 normal because, again, normality is molarity times number of equivalents. So a 0.1 molar solution times 1 equivalent gives me a 0.1 normal solution of sodium hydroxide, which, by the way, is the base that we are working with today. However, a 0.1 molar calcium hydroxide solution is 0.2 normal. 0.2 normal because the molarity in this case would be 0.1 molar, same as before, but there are two equivalents, there are two reacting bits, so the normality is 0.2. It's 0.1 molar because it only has 0.1 moles in 1 liter of solution, but it's 0.2 normal because I'm getting double the hydroxide ions out of that 1 mole of CaOH2. So the normality is double because I'm getting a 2-for-1 deal for my hydroxides. A 0.5, just so we are feeling comfortable with this concept, a 0.15 molar sulfuric acid solution would be 0.3 normal. 0.15 times 2 equivalents coming from the 2 proteinizable protons in H2SO4. And a 0.5 molar phosphoric acid solution is 1.5 normal. There are 3 equivalents in H3PO4 coming from the 3 hydrogens that it's capable of donating. So in order to calculate normality, I am doing molarity times equivalents. So 0.5 molar times 3 equivalents gives me the 1.5 normal solution. So that is the idea of normality, and that is the idea, that is what the concept of equivalence, the reacting bits. And I do refer to it that generically because it can be hydroxides for a base, it can be H's, proteinizable H's for an acids, and it can be number of electrons in a redox reaction. Now, the acid that we're dealing with today, the base that we're working with is sodium hydroxide. Sodium hydroxide has one equivalent. The acid that we're working with is KHP. Potassium hydrogen phthalate, KHP. The important things that you need to know about KHP, first of all, here's the structure. You will need to determine the molecular weight of KHP, which I'm not going to do for you because you are capable of adding numbers on your own. What I will tell you, what is an important piece of information about the KHP, is the fact that it has an acidic hydrogen, and it only has one. All the other H's that are on the KHP are not acidic, meaning that the bond between them and carbon, because they're all bonded to other carbons, it will not break. Those hydrogens will not be donated. So there's only one acidic hydrogen. It is monoprotic. Hopefully, based on the last discussion on the previous slide, you are understanding then therefore that if this is a monoprotic acid, it has one equivalent. It only has one reacting bit. It only has one hydrogen that is capable of being donated. So in 1 mole of KHP, I would have one equivalent. Now, equivalence point. Let's start to get into some of the math behind it. I want to remind you about equivalence point. Now, in class, when we do calculations with titrations, we refer to the equivalence point as the point where the moles of acid is equal to the moles of base. In this lab, because we are dealing with normality, and normality is the number of equivalents divided by the liters of solution, I am going to use the actual technical definition of equivalence point, which is when the number of equivalents of acid is equal to the number of equivalents of base. One thing that I do want to make clear about this lab, though, I am dealing with a monoprotic acid. I am dealing with a base that has one hydroxide. Therefore, for this lab, the number of equivalents will be equal to the number of moles of these things. Sodium hydroxide has one reacting bit, so it has one equivalent. So 1 mole of sodium hydroxide is equal to 1 equivalent of sodium hydroxide. Ditto for the KHP. Equivalence point, number of equivalents of acid is equal to number of equivalents of base. This is not something that you can visualize on your own. So in this lab, we are going to use an indicator, phenolphthalein, that changes color at its endpoint. The endpoint is matched up with the equivalence point for this lab. So we will be able to visualize this point where the number of equivalents of acid are equal to the number of equivalents of base, because the phenolphthalein will turn the palest pink. This is going to be part of your precision for this lab. We are not looking for fuchsia. We are not looking for hot pink. If it's hot pink, I'll probably tell you to scrap the entire trial, to dump your waste and start over again and not use those numbers. We want an equivalence point with a palest phenolphthalein pink possible. You can tell if it's pale pink and not colorless by putting a piece of white paper under your flask. That's the best way to tell. And the ideal situation is that it is so pale pink that you have to call me over to ask if it's pink, that you yourself are not sure. I will then tell you to compare it to something that you know is colorless, like water, to put it next to it and to compare the two. And if you see a difference in color, even if it's slight, I'll tell you that it's pink and that you're good to go. We are not looking for hot pink. I will make you toss it out if you go into the hot pink zone for phenolphthalein. Okay, so the first portion of this lab, you're calculating the normality of the sodium hydroxide solution. That's the standardization of the sodium hydroxide solution. Normality, just to go back to the definition of it, which was at the beginning of this PowerPoint as well, normality is defined as the number of equivalents divided by liters of solution. To be clear, because we're calculating the normality of the sodium hydroxide, that means that we need the number of equivalents of sodium hydroxide divided by the liters of the sodium hydroxide. So let's start talking about how we're going to get these numbers. Well, first of all, the liters of the sodium hydroxide solution, we are doing a titration after all, and we're using burettes. Burettes we use to figure out how much volume was added. So this number on the bottom is going to come from your burette. Not directly, because the burette measures in milliliters and this is liters, but that's where it's going to come from. Okay, so the volume, the liters of your sodium hydroxide solution we're getting from the burette. How much volume did we need to put in the NaOH of the NaOH into the KHP so that the phenolphthalein turned pale pink? Whatever amount that is, that's going to be our bottom number once it's converted to liters. So the issue then becomes, how do we calculate the top number? How do we get the number of equivalents of sodium hydroxide? Because the liters of sodium hydroxide we're getting from the lab. Well, number of equivalents of NaOH. Remember, at the equivalence point, the equivalents of KHP are equal to the equivalents of sodium hydroxide. That's the definition of equivalence point, and we're stopping our titration when we get there. So it really becomes about, how can I calculate equivalence of KHP? Because if I can calculate equivalence of KHP, then I know that that number is going to be equal to the equivalence of NaOH. I can divide it by the volume and get normality. The number of equivalents of KHP, think of it as being similar to moles. Grams of KHP divided by the equivalent weight of the KHP. Just like we would calculate moles by doing mass divided by molecular weight, right? Mass over molecular weight is going to give us moles. Similarly, number of equivalents is going to be equal to mass divided by equivalent weight. here's the thing. Sorry, I just wanted to kind of make sure that I didn't have it on here. The equivalent weight of KHP is going to be the same as the molecular weight of KHP. The reason that it's going to be the same is that KHP has one equivalent. So you can calculate the molecular weight of KHP. I know you're capable of doing that. And you need to understand that it's the same as what is called the equivalent weight of KHP. It's going to be the same number because KHP has one reacting bit. Every 1 mole of KHP produces 1 reacting hydrogen. So if we get equivalent weight of KHP, it's the same as the molecular weight of the KHP. Then we're just doing grams of KHP divided by equivalent weight. That gives us equivalence of KHP, which then we know is equal to equivalence of NaOH, which then we know we plug into our normality formula, divide by liters, and get normality. Now, grams of KHP, just a note, you will measure this on a balance. This is something that you're going to be determining in the lab. So the measurements that you are going to be making are right here. Grams of KHP, liters of sodium hydroxide solution. Everything else is calculations, right? Everything else is going to be calculations. Grams KHP divided by equivalent weight, which is the same as the molecular weight, gives you equivalence of the acid. Equivalence of the acid is going to be equal to the equivalence of the base at the equivalence point. So we take that number, divide it by the volume of the base from the burette. That is going to give us the normality of the sodium hydroxide. A point that I do need to make, the volume that you divide by, the liters of the sodium hydroxide solution, you are not dividing by the total volume in the flask, because I'm not interested in the normality of the sodium hydroxide in your flask. I am interested in the normality of the sodium hydroxide that is in your burette. Do not use the total volume. As such, it actually doesn't matter how much water you use to dissolve the KHP in your flask, because I am not asking about anything about the pH in the flask. I want to know what the normality of the sodium hydroxide solution is. You are not dividing by the total volume of the solution. You're only dividing by the volume of the sodium hydroxide, because that's what we're trying to find. That's the first portion of the lab. These are the calculations for the standardization for determining the normality of the NaOH. The second portion of the lab is once you know that, once you've done that, once you've standardized that sodium hydroxide solution, you're going to use it to tell me what is the percent KHP in an unknown sample. I'm going to supply you with the sample. It will contain KHP, which is a solid, along with a neutral salt, and you're going to tell me what is the mass percent of KHP in this sample. Well, it goes back to the idea of percent. That's what you're trying to find. Percent part over whole. In this case, the part that we're interested in is the KHP, and the whole that we're taking it out of is the sample. So let's talk about these two numbers. How are we going to get them? Because once we get these numbers, you're just going to divide them, multiply by 100, and you can tell me percent KHP. Well, weight of the sample, that's straight off of the balance. The sample is a mixture of KHP and something else, and that is what you're going to be measuring out right away. So that's just initially. That's an initial calculation. In order to find the mass of the KHP, the part that you're interested in, you're going to do another titration. You're going to take that unknown sample, dissolve it in some water, and then titrate it with your sodium hydroxide. But this is different from the first titration, because in the first titration you're using pure KHP and trying to figure out the sodium hydroxide. Now you know the sodium hydroxide. Now you know the normality of that NaOH. Sorry, this smartboard thing is really bothering me. Mrs. Julian can't abide bad spelling. 1L in balance. Much better. In order to figure out the mass of the KHP, we're going to use what we know about the sodium hydroxide and work backwards. So, going back to the definition of normality. Normality is number of equivalents divided by volume. All I've done here is rearrange that equation. Normality times volume gives you number of equivalents, just like molarity times volume gives you number of moles. It's a very similar idea. The normality of your NaOH, which you previously calculated in the lab, times the volume of the NaOH, which is going to come from your burette, will give you the number of equivalents of NaOH. What is special about the number of equivalents of NaOH? Hopefully at this point at home you are jumping up and down and yelling at your computer screen that Mrs. Julian, the number of equivalents of NaOH will be equal to the number of equivalents of KHP at the equivalence point. That is what is special about the equivalence point. Moles of acid equal moles base, number of equivalents of NaOH equal number of equivalents of KHP. So okay, we do the normality, which we previously determined, times the volume that we get from our burette. That gives us in liters, we do have to convert. That gives us the equivalence of NaOH. Equivalence of NaOH will equal the equivalence of the KHP. And we can then determine the grams of KHP by once again going back to this idea. Number of equivalents KHP from here is equal to grams KHP divided by equivalent weight KHP, which hopefully you remember from the previous slide. This is the same as the molecular weight of KHP, which again, I am not going to tell you what it is. You can calculate that on your own. So we calculate this, or we determine this from our lab. We know this already. It allows us to calculate this, which we then go back to the original formula and we plug it in here. Grams KHP divided by the weight of the sample, which we get from the balance, times 100 tells us percent KHP. A few notes about the procedure. Again, I'm going to leave these slides up so that you can refer back to them when you're going through your calculations. I will reiterate these procedural notes on the day of the lab, but I do want to make you aware in advance. You're not going to come in, fill your burette, and start titrating. This has to be a very precise lab procedure. There's a difference between determining the concentration of something and standardization. You will be doing standardization. Regents kids determine concentration of something. I would never in a million years call what my Regents students do standardizing anything. Yes, they are determining the concentration of something, but they're not doing it precisely, and they're certainly not doing it terribly well. So the idea of precision, the idea of knowing our results and making sure our results agree to a really, really fine point is what separates standardization from regular old titration. To that end, there are several things that we need to be very careful with in terms of the procedure of the lab. First of all, when you get your burette, you're going to start by rinsing it out with 5 10-milliliter portions of distilled water. We need to make sure that the burette is absolutely clear of any other compound, that whatever lab it was used in previously, that we've completely rinsed it out. And that's what this is. That's what the rinse with distilled water is. So you're going to do 50 milliliters of distilled water total, but please don't do them all at once. Do 10 milliliters at a time, let it drain, 10 milliliters at a time, let it drain, etc., etc. Once you've done that, you still cannot fill it up with your sodium hydroxide solution. You are then going to rinse your burette with 4 5-milliliter portions of sodium hydroxide of your NaOH solution that you will be standardizing. So 20 milliliters total, but again, you're not going to do the 20 milliliters all at once. You're going to add 5 milliliters, you're going to rinse it out, add 5 milliliters of the NaOH, and then rinse it out. The reason for this is we can't add the NaOH after the distilled water rinse, because that sodium hydroxide that we add is going to be diluted. It's going to be diluted by the excess water, and we don't want, and then it would change the concentration of it, and the whole point of this lab is we're trying to determine the concentration. So we need to rinse the burette out with NaOH before we add the NaOH, so that by the time we add the sodium hydroxide that we're going to standardize, we know that it's not going to be diluted by anything else in the burette. So you're rinsing your burette with water, then you're going to rinse your burette with sodium hydroxide, and then you will fill your burette with the sodium hydroxide that you're going to standardize. A note about reading the burette: you always need to read it to 2 decimal places. It gives you to the 10th of a milliliter. You need to estimate to the 100th of a milliliter. Again, going back to that idea of sig figs and uncertainty in measurements, you need to estimate to the first place that you cannot see. You will be calculating normality to 4 decimal places. So you're going to go out to the 10,000th decimal place, to 10,000th place. Please, you need to do your normality to this. That's how we're going to make sure that your results are very precise. Everything that you weigh in this lab, which is going to be the KHP and the unknown KHP sample that's got KHP and some other salt mixed in, you need to weigh it by difference. Now, I will be supplying some samples to you because we need to use the TECHI scales, the scales that go to 4 decimal places, and they can be kind of slow. So I will be massing some stuff out in advance for you, but it's the mass that I provide you with is not the mass of the KHP. It's the mass of the KHP on the weigh paper. So after you add your KHP to the water, and dissolve the KHP, you're going to have to go back and get the mass of that weigh paper so that you can find the mass of the KHP by difference. Everything in this lab has to be weighed by difference because slight masses that get stuck on weigh papers and aren't transferred into the flask are going to make a difference. Additionally, KHP is a solid. It's not a liquid, and you're going to be dissolving it in water, in boiled distilled water, by the way, not just regular old tap water. Good God, no. Make sure that your KHP is completely dissolved in water before you start your titration. Any undissolved KHP at the bottom of the flask means that that's acid that isn't reacting, but that you think is reacting because you're working with that particular mass number. So you need to make sure that your KHP is completely dissolved before you start your titration. And just to touch on the point, boiled distilled water. Why are we using boiled distilled water? Well, first of all, we're using distilled water because tap water has too much junky junk in it, and this is a very precise lab. We need to be very careful about the procedure, and there's too much other stuff in tap water for us to consider even using it. Additionally, the reason that we have to boil the distilled water first before we use it is that we need to get rid of any dissolved carbon dioxide. There is a small amount of dissolved carbon dioxide in regular water. We need to get rid of it because that dissolved CO2, if it combines with water, it makes carbonic acid. The dissolved carbon dioxide isn't really carbon dioxide, it's more like carbonic acid, which we know is unstable. Now, carbonic acid, hopefully you can realize why it would be a bad idea to have carbonic acid in our solution because, hi, it's an acid, but it's not the acid we want. The only acid we're interested in is KHP. We need to try to get rid of any other acid that's in the water, and frankly, there's a little bit of carbonic acid due to the carbon dioxide. Now, if I boil the water, it causes the carbon dioxide to come out of solution because gases are most soluble under low temperatures, again, cold soda. So by boiling the water, it encourages the carbon dioxide to leave and thus gets rid of any carbonic acid that might be in the distilled water. So when you're doing this lab, I will provide you with some boiled distilled water for dissolving the KHP, but I might at some point ask you, or say like I'm out and here, grab a beaker, boil your own distilled water. It only needs to boil for about 10 minutes or so. It's not a very long time, and then the carbon dioxide comes out. But we do need to do that to make sure that there are no other acids than the one that we are interested in. So that ends the pre-lab. I will reiterate the procedural stuff on the day of the lab, but I'm not going to go over the sample calculations because I think that they're well covered here. They're also well covered in your lab handout. Your lab handout goes on about milli-equivalents, and I don't really want you to worry about those quite so much, but it does have general background on equivalents, and it has the formula for normality, and it shows the structure of KHP, so you can figure out the molecular weight from there.